All right, good morning. Let's see. We were discussing about the expressions for current, and actually today what we'll do is look at one very important concept, which will combine with the microscopic quantum mechanical result to enable us to calculate physically measurable currents in lots of situations, and that is I think we understand that that will also help us to understand the reason why what drives the current to flow, and in the end it has to do with equilibrium, and therefore some concepts of quantum statistical mechanics will also have to be brought in, and essentially you probably have seen most of these concepts before, but we are going to present it in a way or develop it in a way that that will be well suited for the transport problem. So just to summarize, in the last class, if we specifically talk about charge current, we carried by electrons or protons or any quantum particles for which we know the wave function. We developed an expression that looked something like this: the charge divided by twice the mass of that particle, psi. I think there was psi star momentum operator psi minus psi momentum operator psi star. Like that. We derived this from the time-dependent Schrodinger equation, and after kind of deriving it, we said that, well, if there are many states that are occupied, and I know the psi of each individual state, the eigenstate of the individual eigenstates of the system, then to find the total current, I take this and I sum it over all, right? And in addition to that, I had to introduce this concept that I add this occupation function here, right? So meaning if the state is occupied, then only then there's a particle that's carrying a current, and therefore we had to multiply it with a sum f of k, and k being an index for the quantum states, and those are the things we're going to make much more precise today. What is this k? How are we going to sum? What is that f of k? And essentially we'll kind of this is kind of the expression that I'm trying to develop. So, and here current is always going to be a vector, and the momentum operator, I think you realize, it's a vector operator. It looks like minus I h bar gradient, right? So just as a basic, just as a sanity check, the wave functions in this formalism are scalars. Right? Wave functions are complex numbers, right? And the momentum operator acts on a scalar function and converts it into a vector and gives it direction, right? So and in the later part of the course, we will also make the wave function a matrix or a vector when we go into the what's called the occupation number formalism, and we are going to get there. Right now, we are going to essentially develop this idea first. Okay. So what I want to do today is spend a bit of time first, apply to a couple of simple situations, and then I want to spend a bit of time trying to understand what is this occupation function, where does it come from, how does it how do you write down this term by looking at the problem? So that's what we want to develop today. And what I want to stress very strongly is in many of the problems of transport that we're going to be most interested in, at least in this course, what you can change by a lot is this. This is not that changeable. I mean, it is once you have designed your material, if it's silicon, if it is a superconductor, if it's a metal, this part does not change much. You kind of fix it once you choose the material. What changes is this, and this you can change by huge amounts. And I think the Fermi-Dirac distribution, for example, you can change it by 12 orders of magnitude, right? So, and that's what gives you this capability to control current and switch it on to off by many orders and things like that, right? So in some sense, this is control. So we will see that dichotomy as to how it splits, right? So typically, what is said is this is transport and this is electrostatics. So it's interesting. I mean, though we're saying transport, the electrostatics is what controls this function very strongly. In semiconductors, at least, it controls it very strongly. Okay, so let's actually first just apply it in a very simple case, and I'm going to ask you to take it to a little more interesting case based on following up on one of the problems you had in your first assignment. We're going to apply it to a simple case. In fact, right now, let's assume that I'm only applying this current expression for states that are occupied, meaning F is 1. Let's assume that for now. So that much we can. And let's write it as twice mass, and then psi star momentum psi minus psi momentum psi star, right? Now, right off the bat, you can see that if psi is real, then you have no current, right? From here, do you see that if psi and psi star are equal, right? If psi is real, then these two are equal, right? And then therefore current is 0, right? Does that make sense? I mean, do you know situations when psi is real? For example, can you give me an example when psi is real? Wave function of a quantum state of an electron is real. I think, anybody? Yeah.
The ring state you are given in
the ring state? But no, let's see. So if you have a ring state, if I write just e to the power ikx, that's still a state, but it's not real.
The
Superposition. Right. Yeah. So that's right. So if you have an equally left-going and a right-going state, and you have e to the power ikx plus e to the power minus ikx, that's 2 cosine kx, right? With some constants to normalize, etc. So that's real. Similarly, so physically you can see what does it mean? It means you form a standing wave. It's not really propagating anymore, right? So it's really standing, and therefore the current is 0. It's not transporting particles in a standing wave, right? Similarly, if you have a particle in a box, that's the best example, right? All the wave functions of a electron or a particle in an infinite box, for example, all of them are real, right? So if you have cosine, these are all real wave functions. And you apply it, and the current is always 0 because, well, the particle is in a box; it's not going anywhere, right? So the current, by definition, becomes 0, and that's clearly a consequence of that. You can see it right away. The psi star should give you a 0 current. Right? Now, obviously, situations where it's not 0, let's look at those. When, let's say, it's just the right-going wave. So I have only this one, right? For the right-going wave, it's just that one. So we can apply it to just the right-going wave, and you can, basically plop in e to the power. In fact, I want to do it properly. If you have a length L, you wrote in your assignment 2, you can write psi of x with an index of k. That's your wave function. This is the normalization. If L is the circumference, then square root of L is what you need to get mod psi square 1 and I kx. Right? That's your kth state, right? The kth state, and that's your wave function. So you just plug it in, and you have applied it already. A momentum operator acting on e to the power ikx is going to pull out e to the I times k to the front, right? And then there's a minus ih part in the front of momentum operator. They all multiply, and what you get when you apply it is a very nice result. It says your current will be q times 1 over L times h bar k over the mass of the particle, right? So you get plus ik here and minus ik here, so they become 2 times ik, and all 2's cancel, and you get this, right, in the end. And here, because it's a one-dimensional problem, you see this is actually current. It has units of current. You can check it, right? Momentum over mass is velocity, which is meters per second. Charge is coulombs, and 1 over length is 1 over meter. So coulomb over second is amps. So you know right away it's current, right? So it's current per unit, charge per unit time. And you also see something very interesting. It is in a way that looks very much like the Drude form. the Drude form of classical picture of transport? That current density, or is Q times the volume density of charges, particles, the density of particles times the velocity, right? Q and V. I think this is something This is also it's a standard resistor theory, right? The charge times the carrier density times the velocity is current density. And you see it's exactly in that form. This is the charge. I have only one particle in the whole ring, right? So what is my density? It's 1 over L, right? N is 1 over L, so this is N. And what is my velocity? It's momentum over mass, right? So does that make sense? So it is in that form. You can see it, right? So now what we are going to do is try to take it further, because it's just one particle, and then we want to ask, well, what if I had 2? What if I had 10 to the power 10? And that's where we start running into the question, well, then can I put all the particles in one K state, right? And that will immediately lead to a little deeper questions, and that's what we want to spend time on today, right? What is this f of k? How do you find that once you have more than one particle? So, and then that's something we want to discuss. But actually, before I do that, you can see that if I had a number of particles, a number of states, k states, and if each k state had a certain occupation function, just like here, you can see that this whole term here, the transport term, is going to decompose and give you effectively. Let me just try to write what I'm saying now. So applying this same strategy that we did here for just one particle, if we take it to many particles, this expression essentially starts looking like this. So each k state is going to contribute Q. And there'll be some volume normalization factor. This is in 1D is 1 over square root of length. If it's 2D, it will be square root of area. 3D, it will be volume, etc. So there'll be some volume normalization factor, and you see there will be square root of volume once and twice. So the 1 over volume will come up in the denominator in general, right? Any dimensions, right? So I'm just writing it as L to the power D, where D is the dimension, right? Since if D is one dimension, then, well, D is 1. Just like you saw, it's L here. If it's 2 dimensions, it will be L squared, effectively area. And when I say L squared, it means width times length. It's not really, it doesn't have to be a square. It can be a rectangle or any such thing. So there'll be an area here, and you will get, instead of amps, you'll get amps per meter or milliamp per millimeter, right? And similarly, volume, etc. 3D will be amps per centimeter square, right? So it will become centimeter cube. And then inside here, what we got as h bar k over m is the velocity of an electron. Now, this is a very general concept, and so for a free particle or a particle in a ring, for a free particle, we know that the energy versus k. This much I'm assuming you understand very well. Energy versus k goes as h square k square by twice the mass, right? Free particle. And once you put it on a ring, it still looks like that, except your k points are now discretized to it's finely discretized depending upon the circumference, right? But the shape is the same, right? And you can ask the question that for a free particle, if I look at this state here, state k, you can ask what is the velocity of that state. And when I mean velocity, I mean, well, you take the so what's the expectation value of the velocity? That's what we really mean, because again, right? And the velocity for that state for a free particle happened to be h bar k over m, right? And the quantum version where it came from is you apply this relation that the group velocity at any k is 1 over h bar times dE by dk, or the slope of the EK diagram, right? Energy versus k, which is the band structure. In general, what you write it as is, this is the group velocity of any state. This is a very important result, and it's at least looks intuitive, but if you put an electron in a crystal, in a metal, in a semiconductor, some material, actually this is, it remains true no matter how complicated the periodic crystal. And it's very interesting. It's a very, very powerful result, which is why it's a very powerful result, that It's true for a free particle because for a free particle you take the derivative of this and you get that right away, right? It's squared k squared by 2m, and take a k derivative. It's a derivative in k space, a gradient in k space, not in real space. So yeah. And I think the group velocity concept essentially is very similar to the group velocity of light, where you have dispersion, you have many wavelengths mixed up in a mode, and then it's the same thing. It's a similar idea, and it's not a coincidence really, because electrons are being modeled as waves. That's the new thing from classical mechanics anyway, right? So this is very important, and this, I think, in most textbooks you will find this, Kittel and Astro Mermin and others. But actually, in the last 14, 15 years, there's some other terms which we will talk about later. These are related to the curvature and geometric aspects in K space, like topological insulators or some other materials. There's another term here related to curvature, right? But we will talk about that when the time comes later on Thursday. But right now, this is the group velocity. And what I'm trying to say is really, I'm trying to generalize this result by saying that I'm going to, when you apply this current operator here on the wave function of an electron, not just which is free or on a ring, but even as complicated as in a crystal, right? What this will decompose to is the group velocity. Okay? Right? Just like it gave you the velocity here for a free particle, for the most general case, it will become the group velocity of that. Okay? So group velocity times the occupation function of state K. And that's kind of a very general expression for current density. I'm saying, so does that make sense? I mean, it's you can apply to many situations, not just a free particle, right? And what we are trading off here is typically in many materials, metals, semiconductors, insulators, etc. We do know from various measurements, from various things, what is the E of K. We know the band structure, right? From various experimental probes, and also, so we know E of K for a metal, for example. So for semiconductors, there'll be gaps and all that. We know the E versus K, right? We know that, and as a result, what we say is, I'm going to trade off. I'm not interested in writing the wave function because I already know E of K. I know my group velocity, right? I don't want to write the wave function all the time. Right? Does that make sense? So we trade off the wave function. We rather have the band structure EK, and we go with that, right? And that's typically a much easier approach to transport, and not just easier. It's yeah. So as you can see, the wave functions are not unique. They can be expressed in many combinations and all that. But the energy eigenvalues are definitely unique. So there's also that aspect to the story. So so this is kind of an expression we're going to use quite often, and so you can find the group velocity of each state. And so it's essentially now, instead of this, let's say you have silicon, and you ask what is the current flowing in silicon. In silicon, the EK diagram is not not as simple as what we plotted, but it looks something much stranger. It would look something like that. E versus K. For silicon, here's a conduction band minimum. Here's the valence band maximum. These states are all filled. That's empty. And you can put one electron here with field effect or something like that. And then you can apply a field and ask what is the current flowing. Then what you consider is, you look at those states, find their group velocities for each of those states, whatever states are occupied. Find their group velocities, find the occupation functions, and then apply this, and you get the current, right? So does that make sense? I mean, that's the procedure. And okay, so a little bit later on, I will. So this is kind of what I was trying to say. It's a very, very useful result, extremely useful, and it will help us a great deal in this course. Now, a couple of more things. Each of these states can hold. It's a state for electrons, for example, and it can hold an upspin and a downspin, right? So it can have two spins, Therefore, what we say, we can pull that out. You can either leave that in there, or you pull it out and say that I'm going to pull out my spin degeneracy here, right? If my material is not magnetic, then every state of energy can hold an upspin and a downspin, and its energy is not going to change, right? So every state can have a spin degeneracy of 2 if it is not magnetic. So that's spin degeneracy. If it is magnetic, then you have to have a little difference. If it has some other aspects in a topological insulator, then plus k can be upspin and minus k can be downspin. And, so the spin gets locked to the momentum and those sort of things. But this is for a non-magnetic, non-topological material. You can pull out the spin. And similarly, there's another quantity called the valley degeneracy, meaning in k-space, for example, for silicon, this is one point in k-space. If you look at the other, if you're going in the 1, 0, 0 direction and you go to the minus 1, 0, 0 direction, you'll see that it's a mirror symmetry. So, there'll be another valley here. And in fact, there are 6 of such valleys. Right? So it's a valley degeneracy. All it's saying is if I kind of cut through this energy state, how many valleys are there in k-space? And there are 6 of them for silicon. For gallium nitride, there's 1. Right, and so on. Graphene 2, and so on. Right. So the valley degeneracy, you can pull that out as well, just so that we are counting. We are not losing, any of the states. We account for all the states. So that's just, we have to keep that in mind. Okay. So, and I will come to this aspect, of how do we go from, this, and where do things like these differences come from? That we are going to discuss now. Right? So, any questions here? I think just to show that this whole quantum version of current leads to a very familiar expression for current, right? And then we kind of generalize it and say that and realize something very important. All this stuff that you might have done, if you know the band structure, almost there. I mean, any question you can answer very fast by just applying this. So. But what lies from here to there is really the question of what is f of k, right? I mean, that's the major question. And I want to spend some time today doing that, discussing about this. What's the occupation function? Where does it come from? And how does it control transport? And actually, that is really what is the major factor controlling transport, the occupation function and the idea of equilibrium. Any questions on this? Yeah, okay. If not, let's go in that direction and ask what is this occupation function? How do you find that? How do you think about what are these occupation functions, right? So it was clear that if I had only one particle in the K state, I don't have to worry about much of the details. But immediately once you add 2, you run into this issue of can I do that? How many can I put in one state? And these questions, right? Because I need to know how many particles are there in the K state to find the current. Right? Now, I mean, the way it's written, we kind of get ingrained that f of k must be less than 1, but that's not true. I mean, f of k can be 10,000, right? Depends on the nature of the particle. Right? It depends on what sort of particle we are talking about, right? And to kind of approach that question, we can start looking at, going back to the idea of the wave function for the electron. And so let's look at a particle in a box problem, or a harmonic oscillator, or anything that has discrete energy levels to start with. This is just to simplify things. And you have, this is say energy E1, E2. And so on. So one of the things if you look at the particle in the box, is that the wave function is different for different energy eigenvalues, right? So that much we have seen it. Right? So for maybe this is a harmonic oscillator. Clearly the spacing is not quite equal. So here this has a wave function that looks like this, and this, and so on, right? So those are the wave functions of a particle. And another word for the wave function in 3D or quantum chemistry, they call it an orbital. Right? It's the same thing. Right? So the orbital is same thing as a wave function. Right? So if you are in a hydrogen atom, this would be the s orbital, 1s, 2s, 2p, and all these other things. Same thing. I mean, it's just a different name, and from a harmonic oscillator particle in a box, the shapes of these orbitals will change, but the concept will not change. Whatever we're discussing will all stay exactly the same. Right? So these are all orbitals. And now what we are asking is, let's say I start with, and this has a certain orbital wave function, psi 1, psi 2, and psi 3, and psi 4. Right? These are the orbital eigenfunctions. Does that make sense? I mean, sine, cosines, or e to the, or something like this for the particle on a ring. These are the eigenfunctions. Right? So now what you're asking is, can I put two particles in the box, right? And rather, what will, if I put two particles, what will be, the situation? How will it look like, and those things? So what we are really asking now is, when I put two particles, I don't have two wave functions. I have only one wave function. Schrodinger equation doesn't tell you that there are two wave functions. There's only one wave function, right? So that same wave function must capture the fact that there are two particles. Does that make sense? There's only one function, and right away you see that. Let's say, I'm a priori. Let's say that I put one particle here, another particle in that orbital. Let's say, okay? And this particle is at. Let's look at this. One particle is at. The average value is at x1, the other is at x2. For argument's sake, I'm trying to say, how do you compose the wave function? How do you write the total two-particle wave function or a multi-particle wave function? Right? So what we are saying is, the wave function, if I have two particles, must have wave function. Time-independent Schrodinger equation depends only on space, right? Psi of x of psi of r, right? So it depends on space. So if I have two particles, it must contain the locations of the two. This, right? Does that make sense? Just like, if I have two, this is x, there must be x1 and x2. Both particles, where are the coordinates of them? It must have both of them, right? And I'm putting it in two different orbitals. Again, doesn't have to be different, but just for argument's sake, we're saying it's different. So now, how do I write it? Now I know that particle 1 has, wave function looks like this. Particle 2 has wave function that looks something like that, right? Does that make sense? So how do I compose the many particle wave function for this two particle situation? So that's the question you ask. And then immediately you can, so it's not obvious, but the answer to that is it's a product of the two wave functions. This is a product, not the sum, not this, but it's a product of psi 1 and psi 2. And if that's not clear, the way to really look at it is going back to the time-dependent version of wave functions, right? If you remember, for eigenvalues, it looks like e to the power minus e over h bar t times the space-dependent part. That's the full-blown version of the wave function, right? And when I have two particles, the one thing you know for sure is the total energy is the sum of the two energies. That much you know, right? If I have two non-interacting, let's simplify things right now, two particles, one with energy E1, the other with energy E2. Then for particle 1, single particle state, this will be psi 1, this will be psi 1 at x1. Make sense? Okay. For particle 2, the total wave function will be similarly, e to the power minus I E2 over h bar t psi 2 of x2. So it will be something like that. And you can see the only way you can get a state here such that the total energy is E1 plus E2 is you multiply the two. Right? Then you get the total energy is E1 plus E2, right? And you can see that there are some issues in this process itself because, what if they're interacting particles? What if they have very strong interaction? And because of interactions, the total energy is E1 plus E2 plus something, right? Or minus something if it's attractive interaction and repulsive interaction. Let's keep that complication for a little bit later, right? That's what's going to look at, start pushing us towards what is correlated effects and when particles get correlated and such. But from this picture, at least you can see that the total wave function or the two particle wave function will be something like psi 1 x1, psi 2 x2, something like that, right? Does that make sense? From just from this picture, you have to multiply them. And please stop me if any of these arguments are not, not clear or convincing. But that's the spatial part of the wave function. And now, and actually, you have to just normalize it. And if it's a normalized wave, if you need to normalize it, just normalize it. But now, what I'm not that interested in normalization as much as can it really represent the particles we are interested in? That's what I'm really more interested in right now. For example, this particle, if this particle was a proton, and this is an electron, and you can see mixing up various different things because I solved the energy situation for one particle, but you could have solved it for different, there are two different particles, a proton and an electron. Right? And if this was a proton and then this was an electron, this would be actually a perfectly acceptable wave function. Okay? And the reason for that is they are completely distinguishable. Right? A proton has a different mass, a different charge than an electron. Right? So they are distinguishable particles. As a result of that, you can say, that this is a proton, and it has a label of x1 and psi 1. You can say that, right? And this is an electron. It has a label of x2 and psi 2 and psi 2. Does that make sense? They're distinguishable, right? But if both of them were electrons, and that's kind of the most fundamental aspect of this story, they are completely indistinguishable. Two electrons are completely indistinguishable from each other. Right? And these are fundamentally indistinguishable particles. In fact, what is distinguishable and indistinguishable comes down in nature to this. This is it. If you have two particles which you cannot tell apart at all, right? Then you can see that I actually cannot label it like this. Like what is 1 and what is 2, right? It's not because does that make sense? I mean, you cannot just say this. And then the reason for that, mathematically, how do you prove that? You say that, well, if they are indistinguishable particles, and this is really what we're getting into, indistinguishable. If they are indistinguishable particles, then if I switch x1 and x2, nothing should change, right? I can switch it, right? x1 and x2, and say where is particle 1 and particle 2, because there's really indistinguishable. If I swap x1 and x2, this functional form must not change, but you can see here it's a problem, right? Because psi 1 could be sine of kx, this could be cosine of kx, or something like that. Do you see that? Right? These are different functions. These are not, this could be a s orbital which looks spherical. This is a p orbital, hydrogen atom, right? And so it's not the same, right? You cannot have them to be the same. Meaning, if I switch x1 there next to there, that's a completely different function, is what I'm saying. You cannot maintain it to be the same, right? And that's why you're forced to go back and say that this is not the entire story for indistinguishable particles. I have to have something else, do something here, right? And the process you call is you symmetrize it. Right? You symmetrize this wave function. And the first way you try is, you can write it by basically flipping them and writing psi 1 of x2. Basically, I'm kind of flipping it again. And psi 2 of x1. Right? I write the sum of the two. Right? You try this first, right? And you see now, if I swap x1 and x2, this becomes that, and that becomes this. And you see, when you swap them, you get this term, right? So this term becomes that becomes this. So the whole thing remains the same. They just swap roles, right? But the function remains the same, right? So that's one possibility, and that is one allowed possibility for indistinguishable particles. Right? Without this term, you cannot satisfy this condition. And the other possibility is now this will I think is in that, so psi 2 of x2, and instead of plus, you put a minus here, and psi 2 of x1, right? And what I'm claiming is this is also allowed state in quantum mechanics, and the reason for that is following. So now if you swap x1 and x2, what you'll see is, let me write it this way, psi of x2 comma x1, meaning I've swapped the two coordinates here, will become minus of psi of x1 comma x2, right? Because this becomes that becomes this, but now you have a minus sign, right? So it became its negative, so, right? And here for the first with the plus sign, psi of x2 comma x1 is equal to psi of x1 comma x2. So that's when I say that the wave function should remain the same, I'm not being very, that's not actually correct. Every observable should be the same. The wave function is not an observable in quantum mechanics, right? But every observable, like current or mod psi square should be the same, right? And here you can see mod psi square will remain, the probability will remain the same, whether it's plus or minus, it doesn't care, right? Mod square is still the same, it doesn't change, right? So from here, you see right away that you can have two situations. There are, or in other words, what it's saying is very profound. It's saying that if you have indistinguishable particles, there is one category of particles that will take this plus sign, right? And there's another category of particles that will take the negative sign. That's what it's trying to say right now, right? And I think, so the particles that will take the plus sign are going to be called bosons. Okay? So and then we're going to, right? They are going to satisfy Bose-Einstein statistics. Okay? And the particles that are going to choose the negative sign are going to be called the fermions, right? Or Fermi-Dirac statistics, right? Like electrons and so on. So that's two classes of particles right away. And for bosons, you can what you can do is you can say that what if I put both particles in the same point in space, let's say, right, or in the same orbital. Can I put two particles in the same orbital? And then you see that, well, all it requires, I mean, there's no problem. You can put as many particles as you want in the same orbital or same point in space, no problem. Right? You can, because there's no issue with that. The wave function is equal to itself. Sorry, what did I write? I write x1 comma x1. Can I do that? And the answer is yeah, sure. I mean, there's no issue with that. And on the other hand, for fermions, if you try to put two particles in the same point in space, or actually also in the same orbital, you see that x1 comma x1, right, has to be equal to minus of psi of x1 comma x1, which is very weird, right? It's saying the function is equal to its negative. And what is that function? Which function is equal to its negative? It's 0, identically 0, right? So what does that mean? It means if I try to put two particles in the same orbital, same state, for fermions, the probability of that, x1 comma x1, is 0. You can't do that, right? It's forbidden for those particles that have chosen the negative sign to put two particles in the same orbital, right? So that's kind of the main result, and that's really the dichotomy that we have. In a way, you can see this very beautifully. The mathematics leads you directly to conclude that there must be these different sorts of particles by arguments and by symmetry arguments. If the axioms of quantum mechanics are correct, I mean the idea of probabilities of occupation, then this must be the case. This logical conclusion, right? That it's predicting that there are two classes of particles already. So yeah.
The only combination, actually, I think it is not definitely the only combination that we can switch the x1 and x2 and get the same result, right? So why don't we have other form of, say, combination of psi 1 and psi 2,
right,
which has the characteristic that if we switch
oh yeah, good point. Yeah. So actually, this is the simplest way, and actually one of the ways to answer this question. You can try many others. Clearly, as you know, I mean, wave functions are not unique. You can try many sorts of other linear combinations. In fact, the moment you go to 3 particles, you have to write it in a Slater determinant, like a matrix where they have, I mean, symmetrization procedure is rather actually, we're going to look at that in quite some detail later. But this is the simplest explanation, and it is one of the basis functions. So you can have many other combinations which are more complicated than this, right? But it's the simplest basis function which shows this argument very clearly.
Is there any particle that has those wave functions? Say just add a square root of 2 over
Yes.
each term.
Right.
It is still switchable, right?
If I add a square root of 2.
And each of those two terms.
Oh, absolutely. I mean, that you can absorb into the size, right? Is that what you mean? Or you can absorb any numerical factor into the size.
What I mean is that
Yeah.
I can give you some other combinations of psi 1 and psi 2.
Right.
Not necessarily a linear combination. Okay?
Yes, yes.
Any combination that can be switchable.
Right. But you also have to, conserve, for example, the energy. You have to make sure that the total energy of the system is also, the sum of the energies of the individual particles, right? So the energy conservation led us to the fact that it must be the product, right? First, right? The total energy is E1 plus E2. Therefore, I must take the product. I can't just take a sum or a log or anything like that. It must be the product, right? And then we applied this indistinguishability criteria and realized that this is not enough. There must be something more, right? But I think, if your question is this the only function? The answer is no. I mean, there are many other linear, it's a vector space after all. I mean, you have many possible, basis vectors. You can take, realize, I mean, this is one of the, if you have picturized the state of, the quantum states as vectors in vector space in the Hilbert space. This is, every vector space has a basis. And you can switch completely from one basis to another basis. I mean, by just linear combinations of these, right? So but only linear combinations, not others. Yeah.
For two particles, this is the only form of putting psi 1 and psi 2 together and keep the energy conserved.
Not necessarily. I can take this and multiply it by e to the power I, kx or something like that. No problem. No. But that's a constant. I mean, that's not. Yeah. So
something that makes sense.
That meaning something else.
Say, just the example I told you, for example, take the square root of one of them.
Oh, square root of the function itself. Square root of the function itself?
The whole thing.
Oh, square root of the whole thing? Yeah. So you can try that. You'll see that the energy argument will not come out right, because the energy of...
I mean, for two particles, it's the only thing that we can propose.
See, with wave functions, the answer is always no. It's not the only thing. There are many other possibilities. But the combination, the way you have written it, this is the only thing. I mean, you can take the product and then you symmetrize it or you anti-symmetrize it. Now, what is that wave function? That can be, many different things. The single particle orbitals can be many different things. Because, does that make sense? Is it? Yeah. Yeah. So, okay. Okay, you can, maybe if it's not clear, we can discuss it a little bit further as well, but after the class. Okay. So we have bosons and we have fermions, and essentially what it's the main result here is I can have as many bosons as I want in any state, in any orbital. For example, if this is the energies of a bosonic, system. Particles that behave Bose-Einstein statistics. I can put 1 or I can put 5 or 100 in that state. No problem with that. So, but if it's a fermion, then I can have 0, I can have 1 and nothing else. Right? Does that make sense? I can have 0, 1 but not 2. Right? Because this is forbidding you from putting two particles in the same orbit. Right? That's the major difference. Right? So immediately we conclude from here that I have, let's say, so I'm going to erase some of these things here. And so I'm going to write N, bosons and N fermions. This is, again, very unconventional, way of writing it, but that's fine. So N bosons, how many can I put in energy state E1? I can have 0, I can have 1, I can have 2, I can have anything I want, right? And fermions, I can have 0, I can have 1, and no more. Can't put 2, right? So that's, and the same thing for all states. Right? for all states. You can put 0, 1, 2, 0, 1. Does that make sense? I mean, this is another way to picturize the conclusion of many particle effects, or the quantum statistics is, or rather, it's a conclusion of the moment you go to 2 or to 3 or 4, anything more than 1, you're led to this result. So one way, what's called the first quantization picture of quantum mechanics is you look at wave functions and you look at it this way. And the second way, which I'm going to just briefly mention now, and then use it to derive a very important result, and then kind of keep it aside till we come back later to it, is what's called the occupation number formalism of quantum mechanics, where you don't think about wave functions and all. What you think is, I have an orbital of which I know the orbital shape in real space, and the wave function is written as actually an operator. I mean, I'm just mentioning it now as a sum of how many what is the occupation number of that orbital? Is it 0? Is it 1? How many how many particles are sitting in that orbital k, right? Times the the first quantization, or the first Schrodinger equation version of this. This is another way to write the wave function in quantum mechanics, and you can it's analogous, but it's much more suited for correlated effects, where n of k is we're going to apply this thing later. It will be what's the it will relate it to creation and annihilation operators, and you can actually count how many states are filled there and how many particles are sitting there. We will come back to this when we look at transport in a different way. But what I want to use now is use this possibilities of how many particles can you put in an orbital to derive the most important result for transport that I mentioned earlier is what is this f of k, right? You can kind of get it from here right away. Once you understand why this is so, and this is the reason why this is so. From there, this next result is trivial. I mean, yeah. Okay, so what we'll do now is see why this why this argument of probability leads to these two different situations, either with plus signs when you account for indistinguishability, the other is minus sign. So, and the plus sign will lead to Bose-Einstein distribution, right? And the minus sign will lead to Fermi-Dirac distribution. Right? Fermi-Dirac would be electrons, protons, and all that. And bosons would be photons, phonons, and so on. Right? Typically, bosons are massless. There's no free mass. I mean, free bosons are massless, like photons or phonons, whereas typically fermions have mass. And I say typically because you can have these hybrid situations like a Cooper pair, which behaves more like a boson rather than an electron, like a fermion. It behaves a little bit more. It's not exactly a boson, but behaves very much like a boson. But it's composed of fermions. So you can put a few fermions together and get boson. Another thing is superfluid helium. So it's the atom itself, the whole fluid, acts as a boson. It's superfluid because of that. And okay, and then one little thing is that plus and minus are not the only things here. You can have e to the power of phase, I phase, which will also preserve indistinguishability, and that's what leads to some of these other aspects of non-abelian or Majorana fermions and all that other. These are new developments, I think. Yeah. But we're going to first look at this in a little more detail now. One more thing is bosons always have integer spin. I have not talked much about spin because I'm again going to do that later, where spin comes from and all. And fermions have half integer spins. Okay? Half integer meaning half h bar or 3 by 2 h bar and so on. Right? But bosons have integer spins, and those results are mathematically rigorously proven. I mean, this was actually proven by Pauli, the spin statistics theorem, that bosons have integer spins and fermions have half integer spins. Now, and before I derive also the result here, one also needs to appreciate just this fact that this what I wrote in the last term, that for fermions, you cannot put two particles in the same state is, that's the Pauli exclusion principle, that, being one particle being there excludes the possibility of another one. And that is also responsible for, if there was no such thing, if there was no Pauli exclusion principle, if there were no particles that chose the negative sign, there would be no matter actually. I mean, all the matter would be the same, right? The whole reason you have hydrogen and helium and, our different atoms is because you can't put two electrons in the same state, and therefore it has to go bigger. I mean, the whole periodic table of elements emerges because, you can't put two electrons in the same state. Does that make sense? I mean, that's the reason for also all this stuff. Yeah. Okay, so now we are going to write down the occupation function, but you can see I'm taking a little detour, but this aspect of the story is extremely important because, as I mentioned earlier, the transport, sometimes we, I think people get a little bit of a wrong impression that transport is all about the transport. It's a lot to do with the occupation number and equilibrium. What is the meaning of equilibrium? And we are going to now derive some of the most important quantitative results about equilibrium. Yeah. And the results will be, again, there are whole courses that you might have done on thermodynamics or statistical mechanics and such, but we are going to distill it down to what we need. Right? And okay. So and I will again, I've added a few more slides here. I'll post these. Here's the idea of equilibrium that we are going to deal with. We're going to first assume for every transport problem, there is something that we call as, basically a very large object with a lot of energy states. All right, a lot of energy states for, if you're talking about electrons, it's a lot of energy states for electrons. If you're talking about phonons, or photons, whatever there are lots of energy states, and it's a very big system. Meaning, it has. When I say a big system, it just means that it's a lot of atoms, for example, right, and a lot of electrons, much more than the system which we are going to consider as of interest to us, that in which there will be transport and such. Okay? So, for example, this may be a semiconductor, and this may be a ohmic contact, a metal that's connecting to that semiconductor. Right? So here's my what in thermodynamics would be called a heat bath or something. I mean, the names have not much meaning, but the physical meaning is there are lots of states there, lots of states. And you can say that, again, I mean, the concept of thermodynamics, that this heat bath has a unique temperature T. This is very thermodynamic concept. What is temperature, right? But I'm going to say, I think we all have some notion of temperature related to entropy, etc. But it has some temperature T. Physically, if you ask me a little more, hand wavy ways, what is the, if I put a thermocouple, what temperature am I measuring? And that's fine. I mean, that's a decent way of thinking about it. And among these states, the heat bath is filled up with particles still a certain level, okay, in energy. It's filled up to a certain level in energy. Okay. And that energy is the chemical potential mu. Mu is an energy in joules or electron volts, whichever units are okay for you. It's filled up, and the states above that, there are states, but they're empty. Does that make sense? So essentially, it's like an ocean here, and then there's a little river or something like that here. So that's the way we're going to look at. And here's the system in which we're going to look at in our transport. This is much smaller than that. It has very few states compared to that one. Much less number of states. And so again, I have, just like here, I have the energies of the states. I'm going to write it in this way: small e1, e2, e3. And the idea here is I have solved my Schrodinger equation. I've already found out what are the eigenvalues of this state, and I'm going to look at that. And now I'm going to let this again, you see, these are names physically. I think you understand what this is. For example, this is a metal, and this is a semiconductor for me, right? For example, right? And I'm going to let them interact with each other. Right? Let them interact with each other. And then ask the question, what is, if this is, I is the label, I is 1, I is 2, 3, these are the labels. It could be K. It could be K. So what is the occupation function of EI? You can ask this question now, right? This is a very well-defined problem. What is the occupation function of that? What does it mean? What I'm really asking is how many particles are sitting in that orbital. That's what I'm asking now. And why would there be particles here? Because it's interacting with a system which is much bigger, and there's a possibility that, there might be particle transfer from here to there, right? Does that make sense? I mean, that's. And now we, in order to answer that question, remember this is when I write F. Typically, we always think it's a Fermi-type distribution. Not necessarily. It could be Bose-Einstein. It could be more than one, too, right? Yeah. And to answer this question, how many particles are there in this state? This is where we invoke the most fundamental law of quantum stat mech, which is the following. So if you have many states possible, that the particles can fill, the system would minimize its energy if the probability of occupation of the ith state is given by the following. So this is okay. Let me write it down. So it's given by e to the power minus. So 1 over. Let me note down beta. I'm going to write it as 1 over kT, or Boltzmann constant times temperature. Beta is 1 over kT. Okay? So e to the power minus beta times okay, so okay, just a second. No, sorry. No. Am I writing this right? And I, minus B. Okay, so we're saying the probability of occupation of any orbital of any energy state here is e to the power minus beta, where beta brings in the aspect of Boltzmann, constant and temperature, e to the, times the energy minus the chemical potential, right, over a certain normalization factor. Does that make sense? I mean, that's. And let me make sure I'm not beta E1. Oh, yeah. So I was wondering why am I uncomfortable with this? Okay. So this should be EI, and I'm going to actually explain this right now. What do I mean by that? Yeah, that's correct. So, now you just go back to this picture for a second and then see what are the physical quantities I've derived, what that I've written here. This, curly EI, I should rewrite this, okay. EI, E1, E2. This, curly EIs are the energies of these orbitals. Yeah. But if I have, two particles sitting in that energy level, the total energy of that, because of that orbital, E1 will be N1 times E1. Does that make sense? How many particles are there times the energy of that orbital? That's the total energy of that. Yeah? And the probability is of Ni particles sitting in that orbital is this thing is the number of particles times the energy of that orbital. Right? Total energy. So essentially, what you're doing, e to the power minus beta. Total energy minus total chemical potential in some sense, right? The more accurate version of that looks like e to the power minus beta, Hamiltonian minus chemical potential times number of particles. But we are going to look at that aspect of it when we do the negative picture, the non-equilibrium Green's function picture. Here, I think this should make some sense. You might have already seen, if you have not taken too much quantum stat mech, just that probability is e to the power minus beta E. And that's Boltzmann equilibrium. What is Boltzmann equilibrium? Boltzmann equilibrium is when you have two systems that are interacting, but you are forbidden to exchange particles. You cannot exchange particles between them. It's very interesting. You can only exchange energy but not particle, and that might sound really weird. How can you do that? And for example, you can look at a solar cell. Here's a solar cell, and here's the sun. Sun has a lot of photons, right? So, and it's kind of, actually, the solar cell is not exchanging electrons with the sun. right? But it is exchanging photons with the sun. I mean, it's absorbing photons from the sun, right? So if you look at only the electron system, the electrons from a solar cell are not there's no current flowing between the sun, I mean the source, or the heat bath, and the solar cell. Does that make sense? That's Boltzmann equilibrium, where the system is not exchanging particles, electron particles here, for example. But when you have complete freedom to move particles back and forth, that's called the Gibbs equilibrium, and this is essentially the Gibbs free energy that goes into the exponential. It's the total energy minus a chemical potential. Right? That counts how many particles you have. This counts how many particles you have. So it's called the Gibbs equilibrium. And I think you realize that when I sum it over all possible states and all possible configurations of occupation, sum of all probabilities must be 1, right? Does it make sense? So therefore, what is this z? It's a normalization factor, and it's basically the sum of all possible minus beta, ei minus mu and I mu, right? Or all possible configurations. That's the denominator, right? So that you get a 1 in the end when you sum up all the probabilities. And you can see this way, the way this is defined, it is guaranteed that the system will have lowest energy possible in this way, because you have e to the power minus 1 over kt, and it's a very strong function of temperature as well, and then temperature plays a role, and it minimizes energy this way. So what we're going to do now is take this and again, hopefully physically, what are these quantities is clear. Beta is 1 over kt. Big EI is the number of particles sitting in that orbital times the energy of that orbital, the single particle energy of that orbital. Ni is number of particles in that orbital I, and then mu is the chemical potential of the heat bath. Does that make sense? Right? Those are the 4 physical quantities sitting right there, and then they capture all these quantities here. And now you ask the question, what is the probability of occupation of EI if my particle has this nature that it has chosen the negative sign in that symmetrization process, and it's a fermion? What is P of EI? And this, you will get Fermi Dirac distribution right away, right? So, and how do you get it? The probability of, how many, when I say probability, so what I'm going to do now is not really the probability as much as what is the occupation function of EI. That's really the question I'm asking. How many fermions are sitting in that energy orbital EI? Right? And that will be determined by 2 parameters. One is the temperature, and the other is the chemical potential. These 2 will completely determine it. Right? And you see, both these parameters have nothing to do with the system. They have to do with the heat bath. Right? The heat bath has a chemical potential and temperature. They will completely determine what the system is. If you allow for particle to be exchanged, it's going to be completely determined by the heat bath. Very interesting concept. And then okay. So what is the occupation function of energy orbital EI? And that's what we're really saying then is, look, I can have, the probability that there is 1 particle or 0 particle times 0 particles times probability that there's 0 particles plus 1 particle times probability that there's 1 particle in EI, plus there is no 2, right? For fermions, there's no 2, right? You cannot have 2. So this is your total. Does it make sense? We are, probability times the number of particles, probability. So we're summing it. And this, 0 times 0 is just that. And then 1 times probability that there's 1 particle is e to the power minus beta. You apply this. If there's 1 particle, big EI is just, EI times 1. Right? There's only 1, right? So you get EI. Minus, here it's Ni, number of particles in that sense is also 1. So I have N times mu, right? And divided by Z is the partition function. Here, you don't multiply with the numbers. You just add the probabilities, P0 plus P1. Right? Does it make sense? So when you do that, you get what is P0? You get e to the power minus beta times, basically 0 times some other quantities. plus e to the power minus beta times this whole quantity here. I should write it correctly. Curly EI is here minus mu. Right? That's your probability of occupation of EI. Right? And e to the power 0 is 1, right? And then you take this down, downstairs, and you get 1 plus e to the power beta EI minus mu. Right? That's the occupation function of EI. Right? Makes sense? So that's your Fermi-Dirac distribution. And let me, okay. Distribution. You can see that actually I have made some assumptions to get here, but first let's see what's the implication. It's saying that if you know the energy of the orbital EI, all you need to do is find your temperature of the heat bath, right? The chemical potential of the bath, or whatever is the system in equilibrium with, and plug it in. You'll get, this is the occupation, but this is how many electrons you have in the ith energy state. Right? Does that make sense? I mean, and it's a very nice answer. You can see it's very, very useful. It will control most of our transport. Right? Now, what are the implicit assumptions I've put into this? One of them, which is extremely important, is, the moment I write this, that E of the ith state is number of particles in that state times the energy of that single particle orbital. What is the assumption? When can I write that? That's right, when the particles are not interacting with each other. Right? When the particles are not, very important result. I mean, very important to keep in mind that there is the assumption that these are non-interacting particles. And the result that we derive here is it's a non-interacting particle result, right? But you know that electrons interact very strongly with Coulomb interactions and all that, right? I mean, let me say, so we'll discuss this why, but it's amazing that actually when you do measurements, if you make a Schottky diode and you measure, and this is exactly the distribution function you will measure, right? That means that, yes, electrons are interacting in many, in general, but in many situations that interaction is extremely weak, or there are other reasons why it overpowers this aspect. It doesn't show up easily. Obviously, there are systems where this will not work. And then you have to add, all these interaction parameters, Mott Hubbard terms and all that other things. But the Fermi-Dirac is a non-interacting result. Makes sense? It's an important point. And what we derived here, if I make a plot of this function, I think this is probably, you've seen it many times, but I'll just try to emphasize again. Fermi-Dirac function, well, it has value of 1 till you hit close to value of 1, it's very large till you hit EI is equal to mu, and then it goes down, right? It goes down exponentially from 1 to 0. Fermi function, sorry, it's a few of them plotted. So for example, the blue one here, this is a Fermi-Dirac function plotted as a function of E minus mu, that one in the denominator, e to the power beta, right? So e to the power 0 is close to 1, and then when you cross over, it goes to this one. So occupied states, occupation, how many particles are in these orbitals? Well, if the energy is much lower than the chemical potential, then there is one particle sitting in the orbital, right? And then when you go much higher than the orbital, when the energy of the orbital is much higher than the chemical potential, is 0. So that's really what it is. And there's a tail, there's always a tail. If you take two different functions and you take the difference, that's what's actually plotted there. So this is for Fermi-Dirac. And I'm not going to derive this, but for the Bose-Einstein, I think you can see what will happen is instead of just 0 and 1, you will go on till infinity. Does that make sense? You keep going, right? 0 times P of 0, P of 1, plus 2 times P of 2, and so on, right? And I think you apply a little geometric progression trick here, and then what you'll end up with is 1 over e to the power beta EI minus mu minus 1. Okay? So that's what the Bose-Einstein distribution, when you sum the whole thing. Okay? And again, this is Bose-Einstein distribution. And you can see this EI, you can just write it as E. We all realize that these are energies of orbitals or states of electrons or photons we are talking about. It's pretty clear what is that energy. It's single particle energy. So that's you can see that this number, e to the power, 1 over e to the power beta minus 1, this, if for whatever reason you make this quantity really, really, small, right? Not negative, but positive, but very small, you can see that this function will go very high. It will, 1 over 0 sort of picture, right? And can blow up, and those are Bose-Einstein condensation. You can put a lot of particles in one state. Right? F is the number of particles. It can be very, very large, 10 to the power something, very large. Does that make sense? I mean, but this, the maximum value is 1. Right? So there's a major difference. And actually, in the last few minutes, we have, again, I obviously have simplified it a great deal, but I mean, whatever I said is actually, hopefully, it's logical. I mean, this is a result which actually in many books they'll spend like 200 pages to derive this result, and the derivation of it is very hard. Actually, I mean, not hard, but it involves a lot of concepts and all. We're just using it here. We're not really trying to justify and all that right now. But once you use it, this is trivial. I mean, it's a natural consequence. It comes out pretty fast after that, right? It tells you what, and again, just so that we are clear, what is this beta? It's the temperature that characterizes it, the chemical potential. Those are determined by the heat path. And now let's look at a couple of consequences of that. In fact, what I'm going to do is look at it in terms of in pictures, and then in the next class on Monday we're going to apply it, and we're going to apply it to actually two different problems. One is we look at the conductance, quantization of conductance, and then we'll look at for example, we can look at a MOSFET, ballistic transistor, and you can explain all that by essentially invoking this result and this result. Combine the two. What is F? What is the occupation function here that you need to calculate your current, right? So combine the two, you can go very far already with these two. But if you understand where they came from, that's the trickier part, right? So let's look at one situation. This is we are going to look at it qualitatively now. And try to understand further what do we mean by this equilibrium, and what is a physically, can you give me an example of this? And here's an example. So for I can take a metal and a I'm not drawing energy levels now, and I can take a semiconductor, and semiconductors, I think we understand that they have actually, let's plot it in terms of energy. Right? A semiconductor will have a band gap. We know that much, and near the Fermi level. And the metal will not have a band gap. I mean, it has gaps, but the chemical potential of the metal is somewhere here, and all these states are occupied for the metal. Below that. And I put in intimate contact with the metal a piece of semiconductor, and let's say I have lined it up such that the gap of the semiconductor. So these are all, okay, so let me sketch it. So these are all filled states in the metal, right? And these are all filled states in the semiconductor now, right? And here's the gap of the semiconductor. I have somehow managed to make a contact such that this conduction band edge, valence band edge, the gap, the conduction band edge exactly lines up with the chemical potential of the metal. Somehow I managed to do that, right? And we also realize that in the semiconductor, what do we mean by the situation is that there are also all these states which are kind of unoccupied. If you have not doped it, these are unoccupied. We understand that part, right? So so now you can see that if I have lined them up in this way, that there is no barrier for an electron to go, okay, so there's no barrier for electron to go between metal and the semiconductor. Do you see that? I mean, there's no energy barrier now. And I have physically, what am I doing? I have a piece of metal and I have a piece of semiconductor, and it's just sitting there doing nothing right now. So this is the situation in energy space, right? But now what I do is I take the metal and I connect it to a battery and apply a voltage V. Right? And the other end of the semiconductor is still floating. I've not connected anything to it. Does that make sense? I've not connected anything to the semiconductor, but I apply a voltage here, V. Now, what does it do to this picture that we just drew? What does it change? At the first thing, what does it change? That's right. So it will change. What do we mean by applying a voltage V? Is you are basically either moving away, taking electrons out, or putting electrons in. That's what the battery always does. It just pulls out or pushes in more electrons. So what it will do is essentially, let's say we applied, let's say we applied negative voltage on the metal. Negative voltage means you're adding more electrons to the metal. So you're going to pull this up so it was, initially whatever there was, you are going to pull it up exactly by Q times V. That's how many. So that many more states of the metal, you're going to fill it with more electrons. Does that make sense? And I think you can see that everything in nature is charge neutral. So these electrons have to have come from somewhere. Okay. And then the way we are drawing it here, you can see that, I can have a float. It's an open circuit, so it has come from somewhere else, right? But what it will do, I'm trying to illustrate here, is the moment I fill it with some electrons, you can see there's no barrier here, right? So as a result, the chemical potential of the semiconductor must equilibrate with that, right? I mean, there's no barrier for charge transfer. So the semiconductor chemical potential must equilibrate with that. Actually, I'm a little bit out of time today, but we will follow up with this picture in the next class. And we will try to discuss why, when electrons go into the semiconductor, we'll discuss why they will actually fill only certain orbitals, not all. And if you don't allow scattering in the semiconductor, the only orbitals that you can fill from electrons coming from here are the ones which have a velocity that is going to the right. You cannot fill the states that are going to the left. Because for an electron to go from the metal into the semiconductor, it has to move to the right with that momentum, right? And so in the semiconductor, you will have right-going states and left-going states. But if there's no scattering allowed in the semiconductor, you can only fill the right-going states from the metal, right? And then we'll put another one here, and that can fill left-going states, and that's when you start getting transport and all that. We're going to look at that in the next class. But we will carry it on from here, and I will post the notes, extra notes, and over the weekend I'll post a new set of assignments for the class. Okay, good. So we're done for today, and we meet on Monday.